So an important concept in the calculus is the derivative, a central concept, and what we're going to do is repeat its definition and then show a real example of how the derivative is used in physics. Okay, so we want to talk first about what the derivative is. And it's an operation on a function. So I'm going to draw a nice generic function here. So I have a graph. There's my independent variable, y, and here's my graph, y equals f of x. Okay. So what is this a graph of? It's a graph of something that increases with x. Okay. So if we take x here, it has a certain value, and as we move along, as the value x increases, the function also increases in a certain way. And you can even see that it stops to increase right about here. It takes on a maximum value. So that's our function y equals f of x. And I just said the function increases with x. That is to say, it's changing with x. And there's a concept that evaluates this change of y with x. And what we'll do is consider a little section of this function. I'm going to call this the point x sub 0. And out to the right here, I'm just going to rename one x. And so we have the f of x sub 0 at this level right here. Okay, let's connect these with dots. And we have f of x at that point right there. Okay. So the function has increased. Let's construct what's called the difference quotient. That would be f of x minus f of x sub 0 divided by x minus x sub 0. And that is the difference here in the numerator, and that is the difference here in the denominator. So this expression here can also be thought of as the slope of that straight line that I've just indicated as a dotted line. Okay. Well, to get to the derivative, we do the following. We'll say f prime of x evaluated at x sub 0 is the limit as x goes to x0, f of x0 divided by x minus x0. That's an operation, and what it actually gives us is the slope of the line tangent to our curve. I'm going to draw that in as a bold line. So that's the derivative as it's given as its formal definition.
All right, ready? Okay. 3, 2, 1, start. 3, 4, 5, 26, 7, 8, 9, 10, 311, 12, 13, 14, 15, 450, 7, 8, 9, 1, 600, 1,
We have a data table here. Time 0 to 60 seconds, volume 0 to 1,060 milliliters. And once again, that was the volume of water in this beaker as time flows. Okay, collection of numbers doesn't tell us that much when we just look at it. First thing we have to do is construct a graph. And here's our time axis in seconds. This is our volume axis in milliliters. And we've already looked at the scale. We'll look at them again. We have 0 to 60 seconds here. So if we're going to call this maybe 30 and 60 seconds, we could have 10, 20, 30, 40, 50, 60, and then we'd 5, 10, 15. There we go. 10, 20, 30, 40, 50, 60. There's our time axis. The volume axis, we're just over a liter, so if we go with 501,000 milliliters, then we can fill in here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's see what this brings us now. 0 and 0 are a good data point. 5 and 180, so that's just under the 200. 10 and 300, 1, 2, 3. 15 and 450, be about right here. 20 and 600, so we're now above here, 600. 25 and 5, 6, 7, 20, that will be about there. 30 and 820, we see a little tendency in there already. 35 and 910, so there's 935. 40 and 990, so we're just under the 1,000 at 40 seconds. 45, we have 1020, slightly above. 50, we have 1035. So these are very small changes anymore. 55, 1050, and 60 at 1060. There's a collection of data points, and they show a definite trend. We started out more or less linear, and they're curving over. We have a downward concavity. So I'm going to draw a smooth curve that characterizes these points. Something like that. What does this curve represent? The volume of the water in the beaker versus the time during which the water was flowing. We just graphed our data. We have this curve, smooth curve, starting at 0, 0, and up to the total volume. We graphed volume versus time, and we now want to come back to the meaning of this in terms of the derivative, which was the theme of the whole talk. So, let's construct a difference quotient as we did before. This time, we have a change of volume over a change of time. Okay. So the difference quotient will be V of t minus V of t0. That's the difference in the volumes. T minus t0 is the change in time. That represents the slope, or the slope of the hypotenuse of this triangle right here. The actual derivative is the limit as t t goes to t0 of this difference quotient. So the slope of the difference quotient given right there, if we come down to this point, which I'm calling t0, then we're talking about the slope at this point here. Slope of the line tangent to the curve at this point that I've drawn right there. That's the derivative. That's the derivative of the function. We can call this dv dt. And in fact, there's also the nomenclature calling this b prime, or b prime is equal to dv dt. That's the first derivative of the slope. Now we want to come back and see what this actually means in terms of our physics. We filled this thing with water. We filled this beaker with water. That was our graph here. If we ask what are the units of this derivative, we go back to the difference quotient, we see we have milliliters divided by seconds. So the units are milliliters per second. Milliliters of what? Milliliters of water flowing into the beaker per second. So we could also say that's the flow rate. That's the rate at which water is flowing through this nozzle. And in fact, it's identical. There's no water being lost, so the water that came out of the nozzle is precisely the water that's filling this beaker. Okay? So we see that the derivative has a meaning independent of just this formal definition. In the particular case that we're studying, we can say that the derivative represents a flow rate. We're going to give it a new letter, r, and that is equal to dv dt. That's the flow rate. It has many applications because we have flow rates of blood through our veins. We have flow rates of water into a hydropower plant. We have flow rates of water irrigating the fields. So there's quite a bit of application in this thing here. I want to come back to the formal situation one more time. We had a function with this concavity downward. The flow rate, that is to say the derivative, represents the slope at this point of contact. If we go further in time, say up to here, we see that that tangent line has a much lower slope. If we were to construct its difference quotient, we would have had a smaller value of that slope as well. Okay, and so at the very beginning of this curve, you say we had the highest flow rate, the largest slope. The slope decreased as time progressed. What we were doing was turning this handle shut, turning this valve shut. We were decreasing the flow rate. The derivative itself is decreasing.